Konnichiwa minasan. In this video, we continue our introduction to eigenvalue theory by undertaking case studies of eigenvalues associated with a selection of 2x2 matrices. The idea here is that we're going to follow the process of mathematical inductive reasoning. The concept of inductive reasoning is instead of studying theory first and then applying general statements to examples, that's called deductive reasoning. Inductive reasoning starts by studying a collection of examples and then finding patterns to create an idea about theory, and then eventually we'll study the proofs. In this case, we're going to study eigenvalue theory for 2x2 matrices by collecting information about various 2x2 matrices, and then we're going to generalize to a more interesting form. Let's begin with a general overview of how we're going to conduct these case studies and what type of information we're going to be looking for. For each 2x2 matrix that we study, we're going to analyze a number of properties about those matrices. First, we're going to talk about something called matrix structure. Specifically, for each matrix, we're going to ask ourselves, what kind of structure does that matrix have? Is it diagonal? Is it lower triangular, upper triangular? Is it symmetric? Is it positive definite or semi-positive definite or not positive definite? Is it invertible? Next, we're going to ask ourselves questions about the algebraic properties of the eigenvalue and eigenvector information for each matrix that we study. We start with the question, what are the eigenvalues and eigenvectors of the matrix that we're looking at, which means we actually have to calculate it. Next, we want to ask how many eigenvalues are there. For each eigenvalue, how many eigenvectors can we find? And then what type of scalars are each eigenvalues? Are they real numbers, or actually they can be complex even for real matrices? Are they positive or negative? Are they zero or non-zero? Are any of the eigenvalues repeated in our analysis? We'll go much further into this, but remember, we're just getting a general overview. So for every matrix that we study in our case study, we're going to study matrix structure, algebraic properties of eigenvalues, and also geometric properties of eigenvalue and eigenvectors. We're not going to just stay with an algebraic analysis. We're going to actually see if we can develop a geometric interpretation and intuition about what the eigenvalue and eigenvector information is telling us associated with the matrix that we're studying. Specifically, we ask ourselves the question, what type of geometric intuition can we build based on the eigenvalue and eigenvector information that we collected? When we think about that property, that ax equal lambda x, we might ask ourselves, for different types of input vectors x, what does the matrix product a times x represent? And if indeed we find eigenvectors a times x equal lambda x, how can we interpret that geometrically? Specifically, we're going to kind of focus on a few different types of geometric ideas. There's a concept of scaling where the eigenvalue either stretches or compresses the original input, but maybe maintains the same orientation. We also have the concept of reflection or flipping orientation, which might happen if the eigenvalue is negative. We have this concept of rotation. So we've seen Givens rotations and we've seen rotational matrices. One of the questions we might ask ourselves is, well, what is the eigenvalue behavior of rotational transformations? And then also we have this concept of projections, which is loss of information. Every time we look at a specific case study, we're going to figure out which of these different geometric interpretations are at play and how do those relate to matrix structures and algebraic structures. I don't want you to worry about all this right now. We're going to answer all those questions for each matrix that we study, but the concept is we're going to study a large collection of 2x2 and then 3x3 matrices. For each collection, we're going to actually analyze matrix structure. Is there special stuff going on with the matrix? We're going to calculate eigenvalue and eigenvector information and then figure out what the algebraic properties are. Then we're going to interpret that information geometrically. After we've done all three of this type of study, we're going to relate them together and see if we can notice patterns. Those patterns later we're going to call theorems, propositions, and definitions within eigenvalue theory. Moreover, as we make connections between the matrix structure, algebraic properties of eigeninformation, and geometric properties of eigeninformation, there are going to be some very, very famous and powerful theorems that allow us to describe the interconnectivity between these for special types of matrices. Those theorems we will prove later on in our introduction. But for now, I want to prime the pump. I want to discuss some of the patterns that are going to arise in the 2 by 2 case, and we'll highlight those in each individual example that we study. The good news is that for 2 by 2 matrices, there are only 4 possible categories of eigenvalue and eigenvector information related to both algebraic and geometric properties. The first type of information is we're going to say that if we have a 2 by 2 matrix, the first category of eigenvalue information is going to be a matrix A that has 2 distinct real eigenvalues. So those are eigenvalues that are not equal to each other, and there's 2 of them. And then 2 linearly independent eigenvectors. So each unique eigenvalue has an associated linearly independent eigenvector. Algebraically, we might write that A has 2 eigenvalues, lambda 1 and lambda 2, and then 2 linearly independent eigenvectors, such that A sub vk is lambda k sub vk. The second category of eigeninformation that might show up is if we have a real matrix A that has 1 repeated eigenvalue, but 2 linearly independent eigenvectors. That would look like A producing a single eigenvalue that is repeated twice, but when we find the eigenvectors, there are actually 2 linearly independent vectors that satisfy our eigenvalue information, with A sub vk equal lambda times vk for both 1 and 2. The third type of 2 by 2 matrix that's going to arise in our case studies is a matrix A that only has 1 real eigenvalue that's repeated and a single linearly independent eigenvector. These matrices are called incomplete. We'll talk about that later. But the idea is when we're studying the matrix A, we can produce a single eigenvalue that only has 1 eigenvector for that eigenvalue. The last category of real 2 by 2 matrix that arises when we're analyzing eigenvalues is a real matrix that has no real eigenvalues, but instead 2 complex conjugate eigenvalues and 2 linearly independent complex eigenvectors. Specifically, we're going to see that for every complex eigenvalue, we have a theorem later that says the conjugate of that eigenvalue must also be an eigenvalue of our original matrix. And then similarly, we have that each of the eigenvectors are complex conjugates together. Please don't stress out about that too much. I promise you we're going to go into glorious detail for each example that we look at, and then take a look at the entire structure as we build this theory. The point of this particular video is to set the stage and help focus your mind as we do our case studies. For every single example that we look at, we're going to do 3 things. First, we're going to analyze matrix structures, algebraic properties of eigenvalue and eigenvectors, and then a geometric interpretation of that information. Next, we're going to try to categorize the algebraic and geometric information, and when we do that, we're going to just say that there are 4 different categories for 2 by 2 matrices. One category is when we have 2 distinct real eigenvalues and 2 linearly independent eigenvectors. Second category is when we have 1 repeated eigenvalue, but 2 linearly independent eigenvectors. Third category is when we have a single repeated eigenvalue that is a real number, and then only 1 linearly independent eigenvector. And then the only other option that we have is 2 complex eigenvalues and 2 complex eigenvectors. Those complex values will actually be conjugates of each other. The last thing we're going to do is relate our analysis and our categories together. When we figure out the type of matrix structures, the associated algebraic and geometric properties, and then we start to categorize them, we're going to ask ourselves the question, are there patterns between matrix structures that arise and the corresponding algebraic and geometric properties that we notice? The answer to that question is yes. If we were only a few hundred years older, we would be famous for the rest of time, because that's exactly what the theory is going to tell us about. With that in mind, for every matrix that we study, please focus on analyzing, categorizing, and relating that type of information so that we can get a sense of how eigenvalues work in the 2 by 2 case. We will start that process in the next video.